Hello, dear students. So this is our another lecture on the differential equations. तो आपको पता होगा कि जो हमारा previous topic था, the previous video, that was about that Bessel differential equation. And in Bessel differential equation, we have already talked about the solution. We have already discussed in classwork, and in addition to that, we have already calculated the recurrence relation from the generating function for the Bessel differential equation. And in addition to that, we calculated the condition for this orthogonality condition because this Bessel differential equation, it basically satisfies that those it's a kind of that Sturm Liouville's problem. And if a differential equation satisfies that Liouville's equation plus the boundary condition, then we can construct a set of orthogonal functions for that kind of differential equation. So in previous topic, we have talked about that we are basically getting the condition of orthogonality from this differential from this equation, because here we have two cases. So first case is that so this if that k is not equal to m. So in that case, this integral a to b zero equal to 0. Right? So we have calculated this. We are basically getting this equation which is called a condition of orthogonality. Right? So this is the condition for right. So this is the condition for orthogonality, right? Now second case is that if k is equal to l, right? So first case is that पहले हमने क्या था, अगर k l के बराबर नहीं होगा, then this integral will be zero, and that is the condition for this orthogonality. And second is that if k equal to l, right? So in second case, if k equal to l, right? So that means that k square minus l square equal to 0, and that integral from a to b right, because second case is that जब हमारा l k के बराबर होगा, so that means our k square minus l square equal to 0. So in that case the integral, so the second part, that is the integral from a to b, this will be non-zero, right? So let's calculate this integral first, right? So we can do one thing now. So let us suppose that our I equal to okay. Okay, so now let us make substitution here. Let us put that x equal to k rho, and that dx will be equal to, right? So we do substitution putting that x equal to k rho here, right? Because our that here this k equal to l here, right? So that means I can rewrite this as, so we can write this without limits. So I will be equal to, so without limits it will be j b r k rho square rho d rho, right? Or this will be equal to integral that, because so it will be jb of x square x by k and dx upon, right? Because our rho is equal to, so from here our rho equal to, that's equal to x by k, and this d rho will be equal to dx divided by k, right? This will be equal to, so our I will be equal to, okay. So I'm basically taking this integral without those limits, so we can give that limits from some a to b or from some 0 to a. So it's up to us, right? So we can choose any limit, because if you remember that when we construct that condition of orthogonality from the recurrence relation of this Bessel differential equation. So we choose that our right hand side, the limits are we are choosing in such a way so that that whole term will be equal to 0, right? So it's up to us. So we can, for the sake of convenience, or you can say that because in order to construct that condition of orthogonality, so that right hand side term will be left hand side term will be 0. So you just check your note, or you can check my that previous lecture. Okay. So we are basically taking this, we are solving this integral so without those limits, right? So we can take that limits later. So first let's solve this. So okay, you can integrate it by parts. So this will be equal to, sorry, this is sorry, I did a mistake here. Okay, so this will be x square by 2. Okay, so I basically take that this as integral part, so it's x square by 2, and this is uh, as it is, and then you differentiate this part, so that's 2 j of x jv dash of x into x square by 2 d of x, right? Okay, so let's further evaluate it. Then I can write that. So I can write this as mm, okay. So first, let me write one more system. So this will be equal to, or I will be equal to, that is, that's 1 by k square. Is it that jv of x? That's correct, right? And this 2 will cancel here. So you will get that x square, huh? So that will be minus integral x square. But this is okay, x square. Then but you already know that. So you already know that this jv of x, or you can say that some function, as I already told you, if we consider some function, it satisfies those recurrence relation. So then we can say that that is basically the solution for this Bessel differential equation. But we already know that jv is our Bessel function, so it will be the solution for the Bessel differential equation, right? We already know that what's Bessel, the form of Bessel differential equation. So that is basically that x square y double dash plus, तो ये हमारी Bessel differential equation है, right? So that means, so this jv of x, that Bessel function, it should satisfy this Bessel differential equation, right? So that means I can write then, because if this, so as this jv of x satisfies this Bessel differential equation, that means I can write then. So we know that, right? So this is clear, because we are saying that this jv of x, it satisfies this Bessel differential equation, or you can say it can be the solution for this Bessel differential equation. So that I can write this as that's equal to 0, right? Now we can do one thing. We can rewrite this as, so I can take this part from here, right? Or you can write that. So what is our x square JV of x? Okay. So let us use it in this equation. So instead of that x square JV of x, उसके बदले में मैं whole term लिखूँ, right? So that means our integral will be equal to, okay? Because x square JV of x के बदले मैंने ये whole term लिखी, so that is our v square. Because so you write with this first third term here, so this v square JV of x. उसके बदले then I write that x square then x this term and this JV dash of x d of x, right? So this is the whole term. Okay, so you can let's further evaluate it. So before writing that, so I can rewrite this term as, so I can rewrite this as, so this will be 1 by k square, 1 by k square. So this is the first term, right? And second term will be equal to, you can write this as, because v is an integer value. It can have any, because like we are putting there n, so it is v is an integer, right? So you can write this as minus v square by 2. So this first term, and inside will be the first term, and then plus 1 by 2. Okay. तो यहाँ पे मैंने क्या किया, जस्ट हैव अ लुक ऑन दिस, जस्ट हैव अ क्लोज लुक ऑन दिस. सो व्हाट आई एम डूइंग हियर, तो यहाँ पे मैंने क्या किया, मैंने यहाँ पे लिखा माइनस वी स्क्वायर बाई 2. तो इफ आई डिफरेंशिएट दिस टर्म, बिकॉज यू कैन टेक, बिकॉज यू कैन राइट दिस एज, तो जब मैं इसको इवैल्यूएट करूंगा तो फर्स्ट टर्म क्या आएगी, इट विल बी ट्वाइस जेवी ऑफ एक्स देन जेवी डैश ऑफ एक्स, है ना? तो फर्स्ट टर्म क्या आएगी जब मैं इसको डिफरेंशिएट करूंगा, इट विल बी ट्वाइस जेवी ऑफ एक्स into then JV dash of x, right? So, but here it is v square by 2. That 2 will cancel here. So that means you will get here. Okay. So I think I should write one more step, because so I think you may get confused here. So better is to write one more step here. Huh? Okay. So let me write it here. Okay. So you can write this as, so I will be equal to, सो दिस इज सेकंड टर्म, तो पहले टर्म क्या आएगी, इट विल माइनस जे बी डैश इसके मल्टीप्लाई है, तो यहाँ पे डी ऑफ एक्स आएगा, डी ऑफ एक्स, ओके, एंड प्लस थर्ड टर्म, सो थर्ड टर्म क्या आएगी, इट विल बी प्लस एक्स जे बी डैश ऑफ एक्स का होल स्क्वायर, राइट, तो प्लस क्या आएगी, प्लस वन मोर टर्म, तो प्लस दैट एक्स होल स्क्वायर, right? So that means I can rewrite this as I will be equal to 1 by k square. Okay, so sorry, it is 1 by 2. Huh? Okay. Right? तो अब मैंने क्या किया, तो पहली जो टर्म मेरी है, तो पहली टर्म ऐसे दैट्स 1 by k square x square, तो वो ऐसी ही है। तो सेकंड टर्म के बदले मैंने क्या लिखा, बिकॉज जो मेरी सेकंड टर्म है दैट्स x square j v dash ऑफ x d of x, राइट, एंड देन x square दिस, तो दैट मींस अगर मैं सेकंड टर्म को ऐसे लिख सकता हूँ, तो अगर मैं इसको इवैल्यूएट करूंगा, तो ये जो टर्म मेरी होगी, तो ये क्या बन जाएगी, v square by 2 इंटीग्रल दैट इज ट्वाइस jvx jv dash of x d of x, right, okay, into d of x, right। तो ये टर्म जब मैं इसको इवैल्यूएट करूंगा, तो 2 और 2 कैंसिल हो जाएगा, इट विल बी v square jv of x, तो v square jv of x jv dash of x, तो ये वाली टर्म है, दैट इज v square jv of x jv dash of x, right। नाउ अनदर टर्म इज, तो नेक्स्ट टर्म मैंने लिखी प्लस 1 by 2 दिस टर्म, राइट, तो अगर मैं इसको इवैल्यूएट करूंगा, तो इफ आई इवैल्यूएट दिस टर्म, तो ये क्या बन जाएगा, इट विल बी 1 by 2 इंटीग्रल, when we differentiate this will be 2x jv dash of x का होल स्क्वायर plus that x square into twice jv dash of x jv double dash of x, right। तो दैट मीन्स यहाँ पे जो ये टर्म है, तो 2 और 2 कैंसिल हो जाएगा, इट विल बी देयर x jv dash of x का स्क्वायर, तो ये वाली टर्म है, so this is this term, right, and another term which comes from here, 2 and 2 will cancel, तो सेकंड टर्म आएगी x square jv dash of x jv double dash of x, तो ये वाली टर्म है, so it is basically this term, that's x square jv dash of x jv double dash of x, so right, so that means I can I can say that I can rewrite that instead of those two terms. Okay. So that means ये जो टर्म है मेरी, ये जो होल टर्म है, तो इसके बदले, तो इंस्टेड ऑफ दिस सेकंड थर्ड एंड दिस फोर्थ टर्म, इसके बदले में ये दो टर्म लिख सकता हूँ, यू कैन चेक योरसेल्फ आफ्टर इवैल्यूएटिंग दिस, राइट। सो दैट मीन्स आई कैन रिराइट दिस एज, Okay, because that you can differentiate this term, then after the integrate, so this will be same term. Or you can say that these are reverse of each other, so it will be simply JV of x, and this will be 1 by 2 x square this term, right? Because when we differentiate this term and then integrate, so it will be same, right? So it will not be same, right? Now, or we can rewrite this as, okay. Now you can do one thing. Now you can reverse these values because we already make one substitution that because we do one substitution that x is equal to that is equal to k rho, because in this case our k equal to rho, right? So that's why you put x equal to k rho, because k l ke badle hai, because this is our second condition, right? Okay. So first condition is basically the condition of orthogonality, and second we basically get one more condition, that's basically condition of normalization. Okay. Right. So that means we can revert these values. So we can revert this x is equal to k rho in this equation. So that means this equation becomes, so we can write this as 1 divided by k square into, okay. So यहाँ पे मैंने क्या किया? I simply revert that value x equal to k rho in this equation. Okay. So that means this will be x equal to k rho, here k rho, then k rho here and k rho here, because this is x square, that's k square rho square, jb dash of k rho whole square, right? Okay. So this is all r. Or you can further evaluate because this k square will cancel here. So you can write that that's equal to rho square by 2. K square plus that. Because you just check this. जरा इसको चेक हम करेंगे, because this k square will cancel, ये बन जाएगा rho square by 2 this term, then again that this is v square by 2k square, so this is second term, and then this k square will cancel, it will be rho square by 2. So this is what I wrote here, rho square by 2, and this v square by 2k square, right? That's it. Now as I already told, we have those limiters, so let us choose limiters from 0 to a, because we take that limit from a to b, or you can choose from 0 to a, right? So it's up to you. So you just choose that limit, you take that limit. Zero to, okay. So in that case, so our I will be equal to, because we need to give the limit to this equation. So जब इसको मुझे इसको limit देना है from that 0 to a, so this will be equal to 1 by 2 into that a square minus. Okay, because we can combine this and this term, right? But limits are from 0 to a, so this will be rho square minus v square by 2, but give the limits from 0 to a, this will be a square minus v square by k square, and second term will be 1 by 2, because the lower limit is 0, so that will be 0, right? And this will be 1 by 2 a square this one, right? Okay. So this condition, this equation, this above equation holds for the negative values of this negative integers also. So that you can take v plus or you can take minus value also, right? So it is valid for both these integers, right? Either you take n equal to this v plus v or you take minus v also, right? Now we have we know that. So we know we can recall. So from so we can recall that one property of this Bessel function is that if you take the negative value of this x, j of x, right? Or you can take here v. So it's up to you. Oh, okay, so better is to write in terms of v because I have already mentioned here that v, right? Now, because x is our k, right? So we need to choose here k. So we'll choose k in such a way so that our jn of k equals 0, right? So what I'm writing, so I'll write now, we choose ka in such a way so that better is to write in terms of okay, because k is basically this k is simply the root of this Bessel differential equation because it already satisfies this Bessel differential equation, right? This Bessel function. And so if you write the nth root for this, so that means we can write then k will be equal to, so if you write for nth root, so it will be equal to k will be equal to some alpha n. So this is the nth root for this because k is already the root of this special differential equation, right? So we can say that the nth root for this will be, so nth root will be that's alpha of f, right? So in addition to that, we have one more recurrence relation. So if you remember that, we have this jn plus 1 of x, so that is equal to and by that x jn of x minus jn of x, right? But since that jn of k a equal to 0, or you can add that jv of k, it's up to you, jv of k, because v or n is an integer. So we can write that j of n plus 1 of x will be equal to jn dash of x, or you can write that j nu plus 1 of x, right? So from this recurrence relation. So that means I can write here then, because x is our, what is the maximum this value of this. So this is the mth root will be that's alpha n, right? So I can write this as, so this will be equal to, or you can write that j v plus 1 of x will be equal to, so that's equal to minus j v dash of alpha, right? So that means jn plus v plus 1 equal to this one. So let's have a look on this equation because we are already getting that our that jv of k equal to 0. तो ये term 0 बन जाता है. Only we are left with this part because jv dash of k, right? So that means our I will be equal to, so our I is equal to, so our I is equal to, that's equal to minus, because just check that because jv of k equal to 0 we can have plus a square by 2, sorry, plus a square by 2, plus a square by 2, that's a square by 2 jv dash of ka whole square, right? Okay, or you can write this as, because this will be equal to that k square by 2, right? And jb dash of k is equal to, so that's minus times. Or you can write this as, or you can write this is the solution, but it is in the derivative. So better is to write in some normal form. Better is to write. So that's why I use this reconciliation in order to convert that the first derivative, that j dash in terms of j. So because j dash of this equal to j of v plus 1. So it will be j v plus 1 of ka, or you can write that alpha dash of, right? So that's what I, right? So which is basically the normalization condition for this, right? Because you can say that, right, when that alpha equal to that, when k alpha or that kx or k rho equal to l rho in that case, right? So we are basically getting this condition, and this is the normalization constant, right? So that means this condition, this is the condition of normalization. Or you can write this as, integral from that, that's equal to, or you can say that because I is already that, जो हमारा I है, that's already that rho jv square k rho d rho, that's equal to a square by 2 jv plus 1 square alpha, right? So this is the condition of normalization, right? So hopefully in our next lecture we are going to discuss, because there were so many topics pending, like if we talk about the Newman function or Henkel function, that's basically, these are basically a kind of that second and this, or you can say that modified Bessel functions. So our next topic will be on this Legendre differential equation, and we can calculate what will be the solution for that kind of differential equation. Before we calculate that, so we need to check whether the singularity that such differential equation had, whether it is regular singular point or not, right? So after that, using that Frobenius method, we can calculate it a solution, and then we can have some kind of generating function which basically generates that Legendre differential equation, and we get some reconciliation from there. And in addition to that, we can have those Legendre, this orthogonal as well as normalization condition for such a differential equation, right? So hopefully in our next lecture we are going to discuss some another differential equation.